Okay, so here is the second part of 12.1, and where we're talking about first derivative and its graphs. So what I'd like you to do first of all is, why don't you go ahead and try this, and these problems here. Take a look at the graph and see if you can answer these questions about that, okay? And then I'll give you a little time to do that, then we'll come back and we'll check the answers. All right, so let's see how we did here. So the first thing is we're looking at where is f of x increasing. So what I'm going to do on this, let me take like something like a color kind of like this, and let's find all the places where it increases. So from left to right, the y values are getting bigger. So right here, you got y values getting bigger from a to b. You got y values getting bigger from d to e, and then from e to f, and then from G to H. So it's just kind of like you're going up a roller coaster. You can think of it that way. All right, so what you should have done here is increasing. You always use open intervals. And what I mean by that is anytime you're naming an interval or a function increases or decreases, you always use parentheses. Okay, so it doesn't include the endpoints. And so what we're going to do on this, we would say it's increasing on the interval a to b with parentheses. And then we usually have a union to get the next one. Now from here you could go all the way d to f. I'll explain something a little bit more about that in just a minute. And then from g to h. Okay, so that's how you would want to do that. Be sure to use open intervals. Now what happens is a function is increasing when the first derivative is positive. So it's got to be strictly greater than 0. The key is you've got a positive sloping tangent line. So what happens too, like if you looked at this point right here, see the derivative right there is 0 because the tangent line has a slope that's 0, so it doesn't include that. And then right here, you're not even differentiable. The derivative doesn't exist at sharp points. So when you're looking at an open interval on increasing, the reason is because of this. Okay. All right, now we're going to go to decreasing. Let me take a different color, say like this orange. Okay, so we're going to go like this. The y values are getting smaller. Now right here, the derivative is equal to 0. So that doesn't count because you're going to be decreasing when f prime of x is less than 0. So it's got to be negative. The derivative can't be 0. So you exclude that point and then you go there. So you would have to name this interval as b to c, then start over again and go c to d. So you do have to do it that way because the derivative is 0 right there. The tangent line has a slope of 0. And then from here, the only other place you'd be decreasing would be from f to g. Okay, so it'll take care of that then. Okay. All right, now the next thing we want to take a look at is local minimums. Now a local minimum generally is going to occur, the function basically decreases, hits a low point, and then starts increasing again. So that's what we're going to look for. So there's several places that happens. One place this happens is here. The other place it happens there. The function decreases, increases, decreases, increases. So those would actually be the only two local mins, so we would just say at D and at G. Okay, a local maximum is going to be the opposite. It's a high point. The function increases, then it changes directions and starts decreasing. So it's kind of like you're going up the roller coaster, hit the high point, then you get sick and you're ready to throw up. That's kind of a bad way to explain that. Then you're decreasing, so you're going downhill. So it's uphill, up the roller coaster. Now you're getting ready to go down. Okay? All right. So what we do here is, if you look at this, if we identify these places, you'd have a max there and a max there. And that's it. Those are the only places where the function increases, then decreases. Okay, so we would say that is at B and that is at F. Okay, now what these things right here, we've already really answered this question. So this part right here, that just means the function's increasing whenever the derivative is positive. This right here means the function is decreasing. Okay, so we've already answered that. So we're increasing number 1. Okay, so that's the same answer. From A to B, and from D to F, and then from G to H. They mean the same thing. And then decreasing would be what we did on number 2. So it'd be the same thing. It would be B to C, union C to D, and union F to G like that. Okay? Okay, now this next thing is, where is the derivative 0? Okay, well that would be wherever the tangent line is horizontal. So you have this horizontal tangent line, and if we go back and if we look at our graph, well, let's see, that horizontal tangent line is going to occur right there. That's one place at F. Another place would occur at D, and then the third place would occur here. So it would be C, D, and G. Okay, now you want to kind of look at a couple of things on this. I'll kind of zoom on this just a little bit here. Okay, right here, the derivative doesn't exist. There's a sharp point right there, so you can't make a tangent line on that. You can't have a definitive tangent line there or there. So there it's not differentiable. Okay, that explains why the answer is what it is. So the derivative doesn't exist wherever you would have sharp points or where you have breaks. So there's really only two places. There's B and G would be the two places where derivative doesn't exist. Okay, so let's make sure I got that right. B and G. Well, hold on. I think this was supposed to be F. Yeah. And then G. So the derivative is 0 at C, D, and F, and you're not differentiable at B and G. So I wrote that down right. Okay, so the next thing is we'll start kind of crunching out some illustrations how you do this. So we're going to look at functions. We're not going to look at the graphs until we're done with the calculus, and we'll do that to kind of help us make sense of this. So if you want to find a critical value, then what you want to do is you want to find where the derivative f prime of x is equal to 0, or it doesn't exist, or it's undefined. Okay, so we're going to start off, when we find critical numbers, you want to go ahead and find the derivative. So that derivative would be 10x minus 10, and that's just kind of standard derivative rules that you've learned. So you want to do that. You want to take the derivative. The second thing you want to do is set the derivative equal to 0. So we take 10x minus 10 equals 0. Solve this equation. So you can add 10 to both sides, divide both sides by 10, and you get x equals 1. So that would be a critical number. Okay. Now when you look at your derivative, the derivative is never undefined. That derivative, 10x minus 10, that's a line. X can be any number in that derivative. So actually the only critical number is x equals 1. So that's what you get. Now what we're going to do is we're going to make a sign chart. All right, so what we do with this is generally if you make a sign chart, just want you to draw a number line. And what you do is you just put your critical numbers on here. So we had a critical number of x equals 1. Okay, that's a place where the derivative f prime at 1 is equal to 0. So that is a place where that derivative is equal to 0. Okay, now what we're going to do is we're going to write down the derivative. So that derivative, f prime of x, is equal to 10x minus 10. And we're going to look at where it's positive and where it's negative. So if the first derivative is negative, then we're going to decrease. If the first derivative is positive, then the function is going to increase. So what we do is we take this derivative and we just use test points. So what I'm going to do is I'm going to use test point. All I got to do is take a number bigger than 1. That's your critical number. And it doesn't matter what number you pick, you'll get the same result. So let's just do 2, and that will be our test point. So we plug the 2 into the derivative. So we do 10 times 2 minus 10. That's 20 minus 10, so that's 10. So that's a positive, so that means that the function's increasing there. Then if we go here, let's take a number less than 1. It doesn't matter what, you'll get the same result. Let's go with 0. Plug into the derivative. So we go 10 times 0 minus 10. That's 0 minus 10. That's a negative 10. So that means the function decreases. So that sign chart will tell you what you need to know about the function increasing and decreasing. So we would basically be increasing from there to there. Okay, just think of that as an interval on the number line. So we would say 1 to infinity, we're increasing. And then we'd be decreasing, and again, it's an open interval. That's why I'm putting a parenthesis there, negative infinity to 1. Okay? Then what would happen on this, if you kind of just look at I like to just have students do this, let's just think about what's happening on this. What's happened is the function's decreasing. Then the derivative 0, then it starts increasing. So you're going to have something that looks kind of like a parabola, so it's going to be a U shape. So you are going to have a local minimum at x equals 1. Okay, now they're asking for the coordinates. So that means you need to take the function, which again is f of x is 5x squared. And then we need to go ahead and just plug in that 0.1. So we'd have 5 times 1 to the second minus 10 times 1, which would be 5 minus 10. That would be negative 5. So you would get the point 1, negative 5 would be a coordinate of your local minimum. Okay. Now there isn't a max. Since the function decreases and increases, there is no maximum. I'm pretty sure, I think on the handout, this was intended to be what is the max, so there isn't one there. Okay. All right, now what we're going to do is we're going to top this off, going to get out your graphing calculator, and we're going to see how this looks. So I'm going to go ahead and just get my calculator out. And what I'm going to do is put in the function. So we're going to graph the function 5x to the second minus 10x. Okay, now we're going to start this. We can go like standard window. So you can go zoom 6 to put it in a standard window. That just means negative 10 to 10 and always. And then you got what it looks like. That's kind of what we thought it would look like. There's another thing I want to show you. If you trace at the critical number 1, then you can see your minimum. So that minimum was at 1, negative 5. Okay. So on your graph, let's just do this. Let's just go to 1, negative 5. Put a dot, and that's good enough. It also looks like we have a x-intercept at 2, and it looks like maybe we have an x-intercept of 0. So this graph is doing something roughly like that. Okay? All right, so you can use your graphing calculator to check and make sense of these things. All right, so that would be an example of how you take a function and use calculus to analyze where there's a minimum and a max. Okay, are we solid? Okay. All right, we'll do several examples of these, just kind of show you different functions and stuff, but the methodology is pretty much always going to be the same. So we want to start by finding our critical numbers. So you want to start by doing the derivative of the function. This is pretty easy. It would be 12x to the third minus 12x to the second. And of course, that derivative of 5 just goes to 0. So that's it. Okay, what you do is when you find a critical number, you're looking at where the derivative is 0 or undefined. All right, now this derivative is always defined. X can be anything. Okay, there's no 0 denominator or anything. You can take any number and raise it to a power. So what we're going to do is take that derivative, whatever it is, we're going to set that equal 0, then we're algebraically going to solve this equation. Okay, so there's several things you want to do on this. Okay, you got to factor. Factor is a real big deal when you're working in this section. Okay, you got to get your factoring down, because if you struggle with factoring, you're going to struggle with finding critical numbers. So you have a common factor of 12, and you take out the lowest exponent since you have an x in both positions. So that common factor is 12x to the second Then this has to be multiplied by x to get this. Notice x squared times x is x to the third, and 12x squared times 1 will give that. So there's your factoring. So what you do is you have two factors. You want to set these two factors equal to 0. You can do this in your head too. I'm okay with that. So you just have 12x squared equals 0. Solve that. X minus 1 equals 0. The solution of this is just x equals 1. So that's a critical number. This one you can do in your head. You have x squared equals 0. Square root both sides. Okay, if you're not thinking about doing it in your head, that's how you do that. So your two critical numbers would be at 0 and 1, and those are the numbers you're going to use in your sign chart. So that's how you would start the problem. Okay, now I'm going to go down and we'll start our sign chart. So what you want to do on a sign chart, start by just drawing a number line. And we want to go ahead and use these two critical numbers. So we have x equals 0, and we have x equals 1. And we're going to plug into that derivative. That derivative is 12x to the third minus 12x squared. Okay, and we're going to analyze this by using test points. Now, to me, it's best to use the factored form. So here's your factored form. Okay, you really get 12x squared times x minus 1. Now, you can plug your test points into the derivative. I just like the factored form. I think it's a little easier to manage that way. So I'm going to start here. You want to take any number that's less than 0. Just keep it simple. Let's use negative 1. So I'm going to plug it into my derivative. So I have 12 times negative 1 squared times negative 1 minus 1. So here's what I do. That's a 12. This thing here is positive. If you square a negative number, you're going to get a positive. And then this thing right here is negative 2. So it's just a negative number. So I have a positive times a negative. Therefore, I have a negative answer, which means the function decreases. All you got to do is figure out is your result negative or positive. You don't have to work it out all the way to get a numeric value unless you want to. Okay, now in here, let's go with 1/2. Okay, don't be intimidated by fractions. We're just going to go 12 times a half squared. You don't even have to work that out. And then 1/2 minus 1. So everywhere you see an x, plug in the critical value. We'll see that's a positive. So you have a positive 12 times a positive number. And then a half minus 1 is negative. So you have 12 times positive times negative. That's negative result. That also means the function is going to decrease. Okay. All right, now let's go to the next place. Let's use a number bigger than 1. Keep it simple. Let's use 2. Plug 2 into the derivative. So you have 12 times 2 squared. 2 minus 1. That would just be 12 times a positive times a positive. That's a positive result. That means the function increases. Okay, that's all you do. So this means that the function would increase from 1 to infinity. Okay, that's where the derivative turned out to be positive. So we just say 1 to infinity there. Okay, decreasing, you have to break this up into two intervals now. You can't say from negative infinity to 1 because, see, the derivative here is 0. So you would have to say on, whoops, I think this is supposed to say decreasing. You would say negative infinity until 0, so all the way out here to 0. So you would have this area there. Then you would have this area here from 0 to 1. And you have to break that up again into two intervals, so you would be decreasing from negative infinity to 0, then from 0 to 1. Okay, now a minimum. Now a minimum means the function has to decrease, hit a low point, then increase. Okay, that clearly happens here. You decrease, increase. So the local minimum is going to be 1 something. A local max, however, the function is going to do this. It's going to increase, hit a high point, then decrease. Go uphill, then go downhill. That doesn't happen. So there isn't going to be one. Okay? All right. Now, what I want to do from here is, let's go to our function. So our function was Let me look at what that was. 3x to the fourth. So we had like 3x to the fourth and minus 4x cubed plus 5, I think, was our function. Okay, so we just need to plug in the 1. So if we do f of 1, that will be 3 times 1 to the fourth minus 4 times 1 to the third plus 5. You can do that in your head. That's 3 minus 4, negative 1. That would be a 4. So you'd end up having 1, 4. Okay? All right, so that should give you the results. Let's go back and let's do the graphing. Again, the graphing, you don't want to do these problems by graphing unless you have to. You want to do it with calculus and then get your calculator out to check and verify and see if you're on the right track. Okay, so I'm going to go ahead and get my calculator out. You can do this with me if you'd like. It'd help you. And let me know if you have any questions about your calculator. So I'm just going to put in 3. Oops, putting it in the wrong place. I want to put this up here. So I'm going to put in 3x to the fourth. Okay, then minus 4x to the third. And then plus 5. Now, some of you guys may have already learned how this kind of goes, like from college algebra. If you have an even degree, and if that number, leading coefficient, the number in front of that highest even degree is positive, that means the graph is going to turn up on both ends. So again, I'm just going to go zoom 6. Good way to start. See if you see any graph. We may need to adjust this, but that looks pretty good. What I'm going to do is change the window. I'm going to go from like negative 4 to 4. Like that. Okay, and then that'll kind of give us a good idea. I just want to get a couple of points on here. You can always go to your table of values. You can go second graph. Get a couple of points. So like clearly there's a point, 0.5. I'm going to use a red color here. There's a point 0.5. There's a point 1.4. And you just start getting all these things that are way out of range. Okay, so I'm just going to just sketch it in. So the graph's going to do something kind of like this. And then we had that minimum. I think we had a minimum at 1.4. Like that. Whoops, I did graph that totally wrong. Yeah, so it goes more like this. I'm just not seeing this right. So it goes kind of like this. You have a 0.05. Levels off. You got a 0.14. Does something like that. So that's where your min is. Okay, all right, very good. So let's take a look at this. There are times when you have to use a calculator on this. So what I'm going to do here is if you went through and did this by the methodology I just did, you probably would run into problems finding the critical number. So we're just going to use a calculator. So first of all, if we do the first derivative, the first derivative of this function is going to be 4x to the third plus 2x plus 1. But then if you set that equal to 0, you wouldn't know how to solve this. I mean, you just really couldn't do anything with this. So what we're going to do is, with this one, I'll show you a couple of ways to just do this one totally with your calculator. So if you run into this situation, then we're just going to go the technological route here. So I'm going to just have you put in x to the fourth. And let's see, we've got plus x squared. And then plus x. Oh, I got that thing totally wrong in there. Shoot. Come on, get in there. There we go. X to the fourth plus x to the second plus x. Okay, and we'll probably just load this up on a standard window. I'll go zoom 6. Just kind of see what we got going on here. That's probably good enough. We probably could zoom in on this. I'm going to change the window. Let's go -5 to 5 on X and leave everything else alone. And let's do this. So it looks to me like the function decreases then increases. So what we need to do is we need to find that minimum. So what you do, write down the keystrokes if you need to. You just go second, and then you go trace, and that opens up a menu. So you want to go second trace, then you want to go down to minimum. So we'll go to option 3, press enter. So you just go option 3, finds the minimum, and then press enter. Now it's going to ask for a left bound. So if you look at the graph, right here is where the minimum is. Use your cursor key to make sure that the dot, the spider, I call it the spider, is getting a little bit to the left of the minimum. When it is, you can press enter. That establishes a left bound. Okay, and then a right bound, we need to get somewhere over to the right of that minimum. So I'm going to use my right cursor key, move the spider over to where it's a little bit to the right. So somewhere in here is good. You can press enter. There's no exact place you put that. You just want to get to the left and right of that minimum. And then it says guess, press enter. There you got it. Okay, so it comes out. So what you'll do is you get this minimum is coming out. Boy, I'm having a hard time seeing that. Is negative 0.385459. So we just use that X value like that. So what we'll do is I'm just going to round this like to negative 0.39. And what we're going to do is we have a point, and it's so small you can barely see this. I mean, it's just kind of over in here is where that minimum is. And your graph is just kind of doing something like that. You can just make a real rough sketch of that. That's the key point. So that minimum is about negative 0.39. It looks like about negative 0.21. So we would say we're increasing. Increasing would be from there to there. So we would just say negative 0.39 to infinity. Decreasing would be in here. I highlight it in blue. So that would be negative infinity to about negative 0.39 where we're rounded. The coordinate of the minimum is this right here. So that would be about 0.39, comma, 0.21. And then there isn't a max. So that's what you do with these things. You want to know how to use your technology. And that's important in applications and business. I mean, once you get functions set up, a lot of times you can use technology in the modern world to find some of these things. Okay, so that'll take care of that. Now we're going to move on to next thing would be first derivative and graphs. This is just kind of a summary here. I'm not going to go over this too much. This just kind of shows you a graph and what the sign chart would look like. So you have a local minimum. This means you're decreasing, and then you're increasing. So the derivative was negative, you're decreasing, derivative's increasing, derivative's positive. This one you have a max. Notice that you are increasing and then decreasing. This one you're always increasing, so you're increasing throughout that, and you don't have a min or max. That's because the derivative will always be positive, but it'll be 0 at that one critical point like there. This is the opposite. Function just decreases, therefore you don't have max or min. That's another possibility. This one, when you have a sharp point, that means the derivative doesn't exist. You would be decreasing, then increasing. Therefore, you'd have a negative derivative, then a positive derivative. This one, again, you have no derivative because of the sharp point. Then you would be increasing, then decreasing. So positive derivative, negative derivative. This one, slope is undefined. The slope, this tangent line on that would be a vertical line, so it has an undefined slope. Then you would be increasing through that whole interval. You would end up evaluating that with two positive derivatives. And then this one is just the opposite. the slope is undefined, and then you're decreasing throughout that whole interval. So you want to look over those 8 cases and make sure you understand that. Make sure that when your sign chart comes up this way, that you would know what the graph looks like. Okay, so let's do a different type of function now. Let's work with this. So first thing we're going to do is do the derivative of this. This is going to require a product rule now right there. That's a product of 2 functions. So when you do the first derivative, you're going to have to use the product rule on this. Product rule goes first times derivative of second plus second times derivative of first. So the first is x. The derivative of ln x is 1 over x. Plus the second is ln x. Derivative of first x is 1. And then you got to do the derivative of minus x, which is minus 1. So I did a product rule there. I did first x, derivative of second, derivative of ln is 1 over x, plus second, ln x, times derivative of first. Okay, x's will cross out. Looks like you're going to get f prime of x is equal to 1 plus ln x minus 1. 1's cross out. Therefore, you get f prime of x is equal to ln of x. Okay, so what you do is you do this now. You set that first derivative equal to 0, or you think about, where is that first derivative undefined? So if you have f prime of x equals ln x, okay, first of all, if you set this equal to 0, remember a natural logarithm just means log base e of x. If you write this in exponential form, you'll have e to the 0 is equal to x, so that's x equals 1. Okay, so that's a critical point. Undefined, well, if you look at ln of x, first of all, x has to be greater than 0. You can only do a logarithm of a positive number. Okay, so when we do our sign chart, we're going to only consider positive x's because the function's undefined if x is negative. So now what we're going to do is do our sign chart. Always just kind of do the same thing, just draw a number line. And this time what we're going to do is we have x equals 0, and then there's no graph there, okay, because the logarithm, you have to do a log of a positive number. Then you have your critical number, x equals 1, and you're just going to do test points. So we have f prime of x equals ln x. And you can use your calculator on this too, is kind of an easy way, I think, to crunch this one out real quick. I'm just going to do it this way. So I want you to notice on this, then if we did like a test point, like say 1/2, that's a number between 0 and 1. If you did ln of 1/2, you'll get a negative number. Okay, so that's a negative, which means the function decreases. And then once you do an ln, if you do an ln of 1, so you get 0. Well, that's where the derivative is 0. That's a critical point. And then if you did the ln of a number bigger than 1, you'll get a positive. So you're going to increase like that. So you can use your calculator to kind of assist you with your analysis there. Okay, so now if you look at the sign chart, we would be increasing from there to there, open interval. So we would say 1 to infinity. Decreasing would be in here, and it would be an open interval again, so it would be from 0 to 1. Local minimum, okay, the graph has to decrease, then increase. Clearly you got a minimum at 1, so it's 1 something. We'll evaluate that and figure that out in a minute. You don't have a max, because a max, the function would have to increase, hit a high point, then decrease, so you don't have one. Okay, so really all we need to do then is just take the function, which was f of x equals x ln x minus x, and we need to just evaluate that function. Now I'm going to do this by hand. I'm going to do this kind of over at the side here too. So if we do f of 1, because we have a local min when x is 1, but we want to find the y value, you just do 1 times ln of 1 minus 1. That's 1. ln of 1 is 0. So that's negative 1. Okay, so that's what you have. You can close it off by doing a quick check. This is kind of always a good thing to do. So graph the function. We have x, ln x, and then minus x. You can do that in a standard window if you want to. Let's see what we got. Okay, it looks pretty good. So you can see the function is decreasing from 0 to 1 and then increasing from there on out. You don't have a graph to the left of 0 like we discussed. Okay, so that should match up everything. Okay, next thing we want to focus on a little bit, these two examples on here, on this page, these are just some basic graphs. And this is a good activity to help and see if students can, understand, some basic connections between the language. So what I always tell students to do on this, now we're going to start by, we're just going to draw a graph. And our goal on this is just to be able to sketch a graph on here. Okay, so the first thing I'm going to do is I'm going to start with these first statements here. Okay, if you have, we have this statement, and this statement. Now, all of those statements do is they give you points. So this just says when x is -2, y is -1. This says if x is 0, y is 0. And this says if x is 2, y is 1. So that's just given points. So we're going to start off just by, well, let's just plot these points. And start off that way. So we have a point -2, -1. We have a point 0, 0. We have a point 2, 1. Okay, that's what that is saying. Now we get into the next thing, the second condition, we get into derivatives. So this is saying the first derivative at -2 is 0. So that means you have a critical number. So you might have a max or min, maybe, not necessarily though. You might have one. And then you have f prime of 2 is also equal to 0. So what I'm going to do, I'm going to put a little note to myself. Hey, the derivative is 0 here. All that's going to mean is I know that I'm going to have a tangent line that's horizontal. I don't know if it's a max or min yet. I mean, the next clue may give us that information. Okay, go to 3. It says the derivative is positive when on the interval -infinity to -2. That means that you are increasing. So from -infinity to -2, the function is going to increase. So it's going to do something kind of like this. Okay, there's no way to tell for sure, but what I'm going to do is just kind of put something kind of like that. Probably do one thing a little differently there. So we got a function that's increasing until it gets to that point. Then it's going to have a 0 derivative. Okay, it takes care of that. But it also increases on -2 to 2. So from -2 to 2, you're going to increase also, it says. So it looks like it's going to kind of maybe do something kind of like this. And then it'll keep increasing, kind of going something like that. And then it also says from 2 to infinity, it's going to increase also. So I see this kind of graph kind of doing something like that. It's increasing from -infinity to -2, -2 to 2, 2 to 0, 2 to infinity. That pretty well has all the conditions you are going to come up with. These problems are sometimes kind of hard for students. I recommend that you just kind of take each clue and just kind of write down what each clue means and then see if you can put it all together. So it's kind of like you're a detective, okay? You're a mathematical detective, and you're given clues, you're finding the missing function. Sherlock Holmes would enjoy this for sure. You're a detective. All right, example 8. So let's see. Let's go ahead and let's get our graph drawn out here at the side. Okay, so first clue just gives points. So this just means when x is -1, y is 2. This means you also have a point 0, 0. and it means you have a point 1, 2. So what you want to do is just, kind of like the last problem, you want to just plot these points out. So we have a point -1, 2, so we're up here. We have a point 0, 0, and we have a point 1, 2. Whoops, I think I put that first point wrong. You have a point -1, 2, 0, 0, and 1, 2. So you have a graph that looks like that. Okay, now we go to clue number 2. Okay, this says the derivative is 0 when x is -1. So if x is -1, all that's going to mean is we just have a tangent line that's horizontal. We also have a derivative being 0 at 1, so that means when x is 1, this point right here, you also have a derivative like that's horizontal. And then the derivative is not defined at 0, so there's a lot of things that could happen. You could have like maybe a sharp point at that point, so you might have something kind of going like that. It'll kind of depend on what the rest of the problem means. Okay, number 3, this just says the derivative's positive, so that's going to mean that you're increasing from -infinity to -1 and from 0 to 1. So from -infinity way out here to -1, function's going to be increasing. So I'm just going to do something kind of like that. Also from 0 to 1, looks like it's going to be increasing also. So I'm just going to draw something kind of like that. Function's increasing. Okay, 4, this says the derivative's negative. That means you're decreasing from -1 to 0 and from 1 to infinity. So I would look at this like this, from -1 to 0, decrease. And then you want that sharp point there, see? You want a sharp point because the derivative, you have no derivative there. That's what it said, the derivative was undefined. Okay, then also from 1 to infinity, you're going to decrease again. You have something kind of like that. So it kind of looks like a McDonald's arch. Okay, how about that? Okay, next thing I want you all to do, I'm gonna pause this and just give you a few minutes. This is pretty important when I'm doing these videos, that you take a little time to do a few problems here and there yourself, and then I'll pause and then I'll give you a few minutes and I'll check to see if you get this right. What you're doing is taking the graph and you're matching it with its sign chart. We'll look at that. Okay, well, let's see kind of what we've come up with here. Now, I'm going to just kind of go like, as I'm putting these together, I'm going to go like this. Okay, so right now the function's increasing. That means you have a positive derivative. Then the derivative is 0 there. Then you start decreasing, so you have that. And let's see, that's 1, 2, 3. So this one would look like you want to find your critical point at 3 that goes positive and then negative. So that looks to me like this matches with E. Okay, that's what the first one is. Okay, second one. Okay, you have a decreasing function, negative derivative, then it increases, so it's positive. Now you have a sharp point, that means the derivative does not exist at 3. So you need to find the one that has no derivative, negative, positive. That looks like that one is B. Okay, so far we got B and we got E. Okay, the next one goes like this. Okay, you have the functions increasing, so your derivative's positive. Now you would not have a derivative there because it has a tangent line that's vertical. And then what happens is it would be positive because it's increasing. The function's increasing everywhere. So you'd have positives everywhere and no derivative at 3. That looks like D. Okay, so that would go like that. Derivative does not exist there. So that one's choice D. Okay, next one, the function is decreasing. So that means you have negative derivatives. However, when you get here, the tangent line is 0. And then you decrease more. So you need to find the one that has a derivative at 3 of 0, and that's just negative everywhere. So that looks like that one is H. Okay, hope you're getting this okay. All right. All right, just write notes to yourself. The next one, derivative's positive. Sharp point, no derivative. Negative, because it's decreasing. So that looks like no derivative at 3, positive, negative. That looks like that one is F. Okay, this one, derivative's always negative. However, it's undefined there. So that'd have all negatives and no derivatives. That's clearly going to be G. And we get to this one, it looks like we have positive derivatives. When we get to 3, we have a 0 derivative. And then positive from there on out. So it's positive everywhere and a 0 derivative. That would be C. Okay, and the last one here, you have negative derivatives. Derivative is 0, then positive. Okay, so that one would be, the leftover one would be A. Okay, and that's it. So how'd you do? Okay, this is kind of fundamental stuff with calculus, and this is what you can use derivatives for, and you want to be able to see the relationship between the calculus and the graph. So that's real important. Okay, let's see. Getting towards the end here of the section, we want to go ahead and do an example here, some few business applications. And so what we want to look at with this one, let's see, they have a revenue. This says this is the graph of total revenue in dollars from the sale of X electric screwdrivers. We're going to write a brief description of the graph of the revenue function, including a discussion of any x-intercepts. Okay, what we're going to do is we're going to do a graph of the derivative. So let's go down here. We'll kind of do A and B together, but the idea is you want to just go out to, you got kind of key points at 1,000, 500, and 0. So what happens is this derivative, you have positive derivatives there. All of those derivatives take on positive values, and then the derivative becomes 0. All right, so remember, we're sketching the graph, so if the value of the derivative is 0, then we're going to have an x-intercept there. Okay, we're going to have a point, 500, 0, on the graph of the derivative. Okay, then you're going to have the function decreasing, so it's negative like that. Well, also what happens on this is you have a big derivative, and it's kind of hard to show this on this screen, but I want you to think of kind of how these tangent lines go. Let me draw a couple of tangent lines here, and I think that might help you a little bit. Okay, so like, see right here, your tangent line's pretty steep. That's a steep tangent line. If you move on through this and you get right here, well, the tangent line's not as steep. So what's happening is the derivative is getting smaller. Although it's positive, it's getting smaller. So what's happening, your derivative starts up here. And this is like almost at a 45-degree angle. Anytime you have a 45-degree angle, the slope is about 1. So roughly, you would be like about there, and then you would just be going down until the derivative is 0. And then same thing happens here. The derivatives, the steepness, see, it changes. And it changes throughout this. So you would end up getting a steeper and steeper thing. So what would happen is the graph would do something kind of like that. So that would be the graph of the derivative, right? And that's good enough. If you're writing a description of that, you're just saying that the marginal revenue has got its biggest value at 0, and then the value of the marginal revenue gets smaller and it becomes 0 at 500. Okay, let's look at this last problem. We got an average cost. So it says, let's see, a manufacturer incurs the following costs: X rain jackets in 1 day. This is an interval you're given. You have a fixed cost of $450, $30 per jacket. Equipment is that. Okay, so we're going to build a cost function out of that. So first of all, the cost function is going to go like this. We'll just say C of X equals, and then there's a fixed cost, so that's just $450. This is a linear cost. It's per jacket, so you would say 30 times the number of jackets. And then the repairs, you would say, would be plus 0.08 x squared. So that's your cost function. Now you want to find the average cost function. So remember, the average cost function is found by taking the cost function and dividing by x. So we'd just have 450 over x plus 30 over x, 30x over x, plus 0.08x squared over x. So you do that. I would go ahead and write this. C bar of x would be, I'd write this as 450, x to the negative 1. X's cross out, so it's plus 30. One of the x's crosses out there, so that's 0.08x like that. Okay, that's part A. So there is your average cost function. All right, and let's see, next thing we want to do is find the critical numbers. So we have to find the marginal average cost. So we're going to do this derivative. So that's going to be negative 450x to the negative 2. That's 0. And then that derivative on the linear term would be 0.08. So your derivative is going to be negative 450 over x squared plus 0.08. Okay, now it says find the critical numbers and then find the intervals on which the average cost per jacket is decreasing and where it's increasing in any extrema. Okay, so what we're going to do is, there's a couple of things. When we find the critical numbers, the derivative, what we're doing is looking at where is this derivative 0 or undefined. So here's the derivative. First thing is we want to go ahead and take that and set it equal to 0 to find a critical number. Where is it undefined? Well, it's undefined when x is 0. So if x is 0, then you're undefined because you have a 0 denominator. Okay, what I'm going to do here, I'm going to multiply both sides by x squared. So that's going to give negative 450 plus 0.08x squared. See, I'm just doing a distributive property. That cancels your x squareds. And that would be 0. Then I'm going to just slide the 450 over to get 0.08x squared equals 450. I'm going to divide by 0.08. So I get x squared is equal to this. Take calculator. We'll take 450 and divide that by 0.08. So it's going to be 5625. Square root both sides. So I can do the square root of 5625. And that'll give about 75. Okay, so your critical numbers are x equals 0. That's where you have no derivative. And then you have x equals 75. Okay, and we're going to do the, let's see, do the sign chart next. So we'll do our sign chart. We'll draw a number line. And we want to look at, let's see, x equals 0. There's no derivative there. And then x equals 75. That's where the derivative c bar prime of x equals 0. Now we're going to do test points. So the derivative is c bar prime of x. That derivative was negative 450 over x squared equals 0.08. That was the derivative. So again, we just do test points. Okay. Well, first of all, out here it doesn't make any sense. Okay, and that's because x represents the rain jacket. So you have to have positive rain jackets. So you don't have to worry about there. So if we just do a test point here like 1, we would just do this. If x is equal to 1, then c bar prime of 1 would be negative 450 over 1 squared plus 0.08. That's a negative number. Now you can verify that on the calculator if you can't do that in your head. So that's negative. That means function's decreasing. Then we can take a test point, say 76. So if we do c bar prime of 76, you're going to have negative 450 over 76 squared plus 0.08. And let's see how that turns out. This one you need to do on the calculator. So negative 450 divided by 76 to the second power plus 0.08. Let's see if we get a positive or a negative. Okay, that gives positive. So that means we're increasing. Okay, so what you would have is you would have your critical numbers would be these two. The marginal revenue or cost, marginal cost would be decreasing. The cost would be decreasing from 0 to 75 and then increasing from 75 to 76. Okay, so that should wrap up this section. Hopefully this helps you get started on this. Mostly it's derivatives, sign charts, analyzing where functions increase, decrease, and that's about it. All right, hope this helps you to learn the material well.